Hello and welcome to Wastewater Wednesday. My name is Orianna Bretschger. I'm the CEO and founder at Aquacycl. And today we're going to talk a little bit of wastewater basics. So you have a lot of options to treat wastewater, but you have to select the right option for the application. And the technologies that are out there today fit a lot of different applications, but there are limitations. So we're going to talk through some of it. The most commonly used wastewater treatment method is aeration based. So what does that mean? Well, just like it might sound, you're using air to treat water. So you got a tank and your wastewater comes into the tank, and then you use a pump to blow air into the water. And what happens is you're going to have a collection of different types of microbes that are in this tank along with the wastewater, right? And they're going to consume those bubbles of air in their process of respiration or breathing, right? They're going to breathe that air, and then they're going to eat all of the wastewater particulates that are suspended, or the soluble wastewater compounds that are suspended within this tank. And as they do that, they grow more and more of themselves, right? These are the little bacteria, because they're using that oxygen as a way to breathe, and they've got plenty of food in the wastewater to eat, and so they get to grow really quickly. Now, this is a very common method. It's used in almost all centralized treatment facilities, and there's a lot of ways, a lot of interpretations of this. There's activated sludge, which is the simplest form. There's membrane bioreactors, which is a little bit more packaged plant, a very efficient way of doing aeration. There's moving bed bioreactors, which is also another version of how you aerate and keep a fixed film of organisms that like to breathe air and eat waste. But ultimately, right, this is the most understood, most applied type of wastewater treatment. However, the limitation is these bugs require a good amount of air in order to grow and to survive. So you have to have a lot of good mixing throughout this tank to make sure that the air gets to the bacteria, right? If you have a really high concentration of waste, if you have a lot of waste in the water, a higher concentration of carbon, that means you have to input a higher concentration of air. And pushing air into water is not the most energy efficient thing that you could do. It actually requires a lot of kilowatt hours to do that. In fact, about 1 kilowatt hour is required to push air into water to treat 1 kilogram of chemical oxygen demand in the water, right? And sometimes it's even higher. It could be 1.2, it could be 1.5, depending on the size of the tank and the efficiency of the pump. So when you have to force a whole lot more air in, that means you have to have a much bigger tank, right? Or you have to have a very efficient distribution system, and then you hit a threshold. There's only so much air you can force into water to actually treat all of the carbon that comes in at a certain concentration. So when you get into aeration technologies, you usually want to limit your inflow to 2,000 parts per million, or milligrams per liter of biological oxygen demand. That's your limitation, roughly, for aeration, depending on the type of aeration that you're using. Lower is better, it's more efficient and smaller. When you're dealing with a concentration that is higher than 2,000 parts per million of biological oxygen demand, now your options are more on the anaerobic side. So that means no oxygen present in the treatment process. And anaerobic digestion is the most common form of this type of treatment. It's been around for a long time, and there's lots of iterations. And so the most basic form of anaerobic digestion is, again, a tank. And you got mixing in this tank. Maybe you're heating this tank to keep the bugs nice and warm. But you have your concentration that is above 2,000 parts per million of biological oxygen demand that's coming into the tank, all right? And so what's happening here is you're not forcing oxygen anymore. There's no oxygen going to be present in this tank, but you do want to have a source of CO2. And what is going to happen in this tank is your bacteria, different types of bacteria now than were in our aerobic tank, right? They're going to take that carbon dioxide and they're going to consume the organics coming in, so that's their food source. But now their respiration source is actually fixing CO2 into methane, CH4. And then that methane leaves the anaerobic digester, and you can capture that biogas, use it as a way to produce energy through a method called cogeneration, where you have to purify the biogas, you burn the biogas to make heat and electricity. You can also supplement natural gas lines with the methane that you capture from an anaerobic digester. Now, the limitations with an anaerobic digester are more space and time. So this process works well, but it typically works slowly unless you have really optimal conditions. And so if you're in a typical digester, sometimes your hydraulic resonance time, or the amount of time that your wastewater has to sit in this tank, can be up to 40 days before you can get most of that water clean. Now, there are high rate anaerobic digesters that can deal with fairly high concentrations of incoming biological oxygen demand. And that could, you can remove a good bit of it within a 10-hour hydraulic retention period, which is awesome. And you get that methane back. But you have to have very good mixing. It has to be heated so the bugs are nice and warm very consistently. And you need to make sure that it's a very even flow of concentration. These organisms are very sensitive to changes in concentration, in temperature, in pH, and variability in the amount of organic or CO2 that comes in. They're a little finicky, you gotta treat them real nice, but anaerobic digestion is a good way to go if you've got high concentrate wastewaters. And a lot of space. That footprint is another constraint. You have to have permits to operate because methane is an explosive gas, so you need to make sure that all of your classifications and your safety methods are in place. But if you're dealing with high volumes of high concentrate wastewater, anaerobic digestion and anaerobic processes are a great way to go. The other methods that are a little bit more simple and can also act as pre-treatment methods to our core aerobic and anaerobic digestion processes are physical separation, right, and pH neutralization. And both things typically have to be done ahead of either aeration or anaerobic digestion method. So what is separation? Well, there's a lot of methods. And it's important when you have a high concentration of total suspended solid in your wastewater. So those are those particulates, right, which may settle to the bottom of a jar if you let your wastewater sit. They're particulates that may actually stay suspended and never settle. But if they go into one of those methods, an aeration method or an anaerobic digestion method, the bugs may not be able to break it down as efficiently, right? So it's good to separate that stuff out so that your technology that you're using to treat the water and the soluble compounds in the water can act most efficiently. So if you want to separate total suspended solid from your liquid wastewater, there's a lot of different ways to go. You can use a centrifuge, which basically your wastewater comes in, you're spinning it, all of your solids move out to the sidewalls of your rotating disc, and then the liquid passes through, and then you have to scrape that disc and bring off the solids and put it somewhere else, landfill, compost, whatever type of wastewater it is. There is a simple screening method, right? So often you have wastewater that'll come in and you've got these little screen. It can be a fine screen, it can be a very open screen, depends on kind of solids that you're trying to catch. And so the debris catches in the screen and the wastewater can drop down, and some of the wastewater will flow over as well. So you've caught a good amount of debris here. And then you might do this a few different times with a few different screenings, right, to catch the smaller particulates. So solid separation mechanically, that's the basics. Then there's also some other methods like dissolved air flotation, which not only helps with some of the solids, but also helps with fats, oils, and grease. Things that won't necessarily sink, but things you want to float. And dissolved air flotation is a kind of a hybrid on aeration and separation, where you're bringing oxygen in, you're bringing air in, and maybe you add in a chemical. This could be like a ferric chloride or a type of polymer. And you get a good amount of mixing, so your wastewater can coagulate with these different compounds, so you get bigger globules of your suspended solid. And then the oxygen can, depending on what you're adding, can help some of these globules float, while other globules will sink. And so then you can take out your sludge and you can scrape off the waste, and then the rest of the water moves through to the next treatment process. And feed.